How to compare the security of code written by humans to LLM-generated code. This video is for you. If you're interested in understanding how to measure LLM-generated code and how to think about where LLM-generated code is going in terms of security. This is the result of a master's thesis by Yasmin Egli. As her advisor, I had the chance to present it in Rennes, France at the staff conference LLM for SE. What exactly are we trying to solve here? Well, the question is, who writes more secure code, humans or LLMs? Why is this question important? A year ago when we started this project, there was still a lot of debate about should you vibe code, should you use LLMs to generate code? And there was a lot of pushback from senior developers saying, no, it doesn't output secure code. So I will not use LLMs to generate code. But then some of the feedback was, well, humans don't write secure code either. So based on anecdotes, a lot of people were debating, okay, who actually writes more secure code? This continues to matter today as we think about at what points should humans intervene in LLM-generated code, and how can we actually build out secure systems? To answer this question, let's at least start with, what does secure code even mean? If we had an accurate way to find and measure secure code, we would find it all and mitigate all the issues, and we wouldn't have any security vulnerabilities. Clearly, that's not the case, so we still have to understand that even existing measures for understanding secure code have a lot of false negatives, a lot of false positives. So what did we do for this particular project? We decided that secure code has to be correct. So it should run without failure and it should produce the expected results. Of course, you can write a very simple hello world program that doesn't have any security vulnerabilities, but it might not be actually useful for your business. So the code has to be correct, it has to execute. We also relied on static analysis, or Yasmin did. She used some of the options that are available in classic static analysis tools to look at cyclomatic complexity, mean function length, and looked for a number of insecure patterns found by the rough static analyzer. Both the complexity and the mean function length in previous work have found to be indicative or maybe correlated with security weaknesses in the code. So let's get to this key question of how do we do a fair comparison between humans and LLMs? And I want to point out this really nice paper by Firestone titled Performance versus Competence in Human-Machine Comparisons. And so this paper takes as an example image and vision machine learning and points out that a lot of the machine learning mistakes just look really odd to us, or typically have looked odd to us, such as blueberry muffins being labeled as puppies. And the machines don't have to pass through the same processing as the human retina. And so perhaps a fair comparison that would mitigate some of these strange perturbations and answers would be to make the machine learning models pass through some sort of model that resembles the human retina in order to make it fair. So there hasn't been a lot of work done on what fair comparison means for secure code or for vibe coding, and that's part of what this work starts to explore. There have been some previous work comparing LLM-generated code, the security of LLM-generated code to human code. I point out 3 here. Here are the titles, what do they give humans versus what do they give LLMs. And what we see with the first 2 is that they are relying on code samples found that humans have already created, but we don't actually know what product specifications or what the humans were given or told to write. We do know what the LLMs were prompted with. Sometimes they get multiple examples. Sometimes they have reasoning, chain of thought involved. We don't know if humans were given the same sort of examples and benefits when they wrote the code. For the second work on this list, the docstring and function signature were extracted from the code the humans already written, and that was given as a prompt to the LLM. So it seems like the LLM's already starting with a bit of a leg up there. The one that's maybe the closest to fair and really trying to give the same prompt to the human and the LLM, unfortunately, they had one person, one student, as the only human who was represented. And we all know that there's a lot of human variability in coders, just as there's a lot of variability in models. So we can't really take one human as an example to represent like all of human coders. So let's talk a little bit about what Yasmin built to create a reproducible, fair environment to test code. This is all open source, online. You're welcome to use it. We would love for people to use it, modify it, grow. So basically it works like this. You start with some text that is your exercise definition. This is exactly what you're gonna have both the humans and the LLMs do. And you send that as a prompt to the LLMs, and you make sure that the humans also get those exact same instructions. You repeat this a number of times to think about latent non-determinism in your LLMs. You can also, we set the temperature to 0, but you can play with that, of course. All the results are stored in a database. The output is saved as text in a code data set, and then for each individual example, a new sandbox is started, the code is executed. The sandbox helps make sure that you get a comparable environment, more or less, every time, and also protects you from security issues. We run the static code analysis, and then you see the last box should be the metrics. It's all saved in the database, so you can run it multiple times and evaluate the answers. Just another quick walkthrough. Let's look at that same process broken down into the 4 steps. We have the task selection, which in this case was a coding challenge that humans got and that the LLMs got. The code generation, this was all automated via the OpenAI API. You can redo this with any model you want. You can even use local models. You can set your input and output parameters based on what actually you want to research, what you're looking at, what question you're trying to answer. As I mentioned, the code was executed in a sandbox for this controlled code execution. The outputs and errors were all saved. And then we evaluated the code with these predefined quality metrics, as I mentioned at the beginning. You can read the paper to get more from this. And so this is repeated multiple times to enable, hopefully, to enable a statistical evaluation of which one is better. How do we compare these? So one of the things we found in one of our design decisions that the code has to be correct created this leaky pipeline. So let me explain it. The LLM responds to an exercise prompt, and the result should be executable code. And if it's not executable code, we can't run it. If it runs with failures, then we don't get the output, right? If the code gives the incorrect answer to the challenge, then we don't consider this valid code. And it's only sort of the remaining code that's left where we actually decided to run the quality and security metrics on. So you may start with a large set and end up with a smaller set of executable code. We do not claim to give this answer of who's better, humans or LLMs. We ran a feasibility study on this framework, and we can tell you some of our lessons learned so that if you want to do similar studies, you can take this into account. So our feasibility study used programming exercises based on real challenges. Yasmin found the 2024 advent of code and some Python security challenges. She chose 13 of them that required a mix of both reasoning and syntactic correctness. She wrote unit tests for correctness to check that the output was correct. We actually had a pretty small set of human code. Yasmin chose about 5 high-ranking Python solutions and extracted their repositories to use this as the human code that we compared to the LLM code. If you are doing research here, you may choose to do this differently. You may choose to find programmer participants for your research study and bring them into a more controlled environment or condition, and to make sure you understand, are they using LLMs? Are they doing it on their own? Are they using books? So you can set up your experiment in multiple ways. 5 LLMs were used to look at code generation. They're all from the same family, but they have some different advertised properties. GPT-4 was considered the stable baseline. These mini and nano models were considered low cost and fast, and then some bigger reasoning models that were advertised to be better at code generation. In the end, we expected the reasoning models to perform the best, but in the end they did not. Let me tell you why. And it's really down to this leaky pipeline. So we had 5 models, 13 exercises, 60 runs each. This ends up with quite a few data points. But then what happened is we needed executable code, but the reasoning models really wanted to reason about it, and they did not just simply output code, but they output a lot of explanations and human text interwoven with the code. So I call this LLM blah blah blah, and to run these examples requires going in and parsing out all the blah 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 that the LLMs are outputting, and even further on, there's fewer examples that were actually correct despite this. Yeah. So here's some findings before I actually show you some of the data. As I mentioned, the reasoning models output more blah, blah, blah. So the output was not executable code. It's something to be aware if you're giving exactly the same prompt to humans as to LLMs, because we did not add an additional prompt saying only output Python, da 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 da. We just gave them the coding challenge. The results really depended on the prompt. So it's really important to think through what are the exercises you're actually giving to the LLM that you want to study. And we found that the LLMs tend to either do really well or really poorly on a prompt, and this creates sort of a bimodal distribution. If you're from the line of statistical reasoning, where you assume a normal distribution and then you sample 2 different sets and try to figure out if they're from the same distribution, it's really hard to figure out how to set up the appropriate statistical test here. So overall, was the code correct? These graphs actually flip. They show the number of errors or failures that were found, and each square is a different prompt, and at the bottom are the different models. And what you can see just visually here is that there's a really big difference in the types of failures depending on the prompt. So the first box shows that this first prompt had resulted in many models just not giving output, like they basically didn't understand it, whereas some other models, prompt 12 had a different set of errors, and some of the prompts basically had no errors. So it really depends on the prompt. Like, what are we actually asking the LLMs to do? There are no human values on this because we chose, or Yasmin chose, some of the best coders from the Advent of Code examples, and all of their code ran without failure. So we do not have a bar here showing 0 for all the humans. kind of the point of this whole experiment was, is the code secure? And again, we're looking at the prompts. The prompts aren't shown if there were 0 security failures. So in the previous example, there was a lot of prompt 2. We didn't have executable code. So there was less code to test for security failures, so there were less security failures. It doesn't mean that that prompt was secure. But you'd still see, again, this huge variability in types of errors based on what prompt it was. In this case, we do see the human. It's the last bar here. And it's a little bit hard to see on the screen, but I do want to point out that the number of errors is different in each square. So some of them go up to 60. Prompt 11, which is the one with only 1 green bar on the right, only has 1 error, so that was 1 human code had an error. So in this case, it looks like that particular prompt was kind of easier for LLMs than for humans, but we're only talking about 1 security error from the static analyzer. So did we answer the question we set out to solve? Who writes more secure code? We weren't actually trying to answer this question, and I would be really disappointed if you walked away from this presentation and said, like, we found the answer to it, because this was really just like, how do you even answer that question? Does our framework work? So don't take these results and sort of quote them to prove that one is better than the other. However, if you needed to make a business decision based on these results, it would largely be you cannot trust your LLMs yet to write secure code. You still need additional review. If you are interested in this question of like, well, how do we actually compare? We did make some progress on methods. We learned some lessons the hard way that you don't have to go through if you want to do something similar. We described a slinky pipeline of our design decision to actually require that the code run and be correct. That results in fewer security errors because there's less code. Yeah, so also the reasoning models, these specific model behaviors broke some of the automated evaluation pipelines. So you have to be aware of that. And then this question of like, we gave the same prompt for humans and LLMs because we thought that would be more fair, particularly to humans. But then it caused a lot of problems with LLM generation. So maybe we went a little bit too far in emphasizing the sorts of exercises that humans understand and are good at, and perhaps not giving the right prompts for LLMs. So still, maybe it was fair, but not equitable, which I think is something to keep in mind for future design. Obviously, limitations. The human data set was small and biased. We only had like good coders. The security metrics did not reach statistical significance. We only looked at Python code in this. You can extend, like I said, this code is open source on GitHub. You can extend it. And the work was carried out in late 2025. Of course, models are changing so rapidly, it's hard to keep up. I think the general lessons of how do you test it, how do you think through comparisons still remain, regardless of which model you use. Feel free to take the framework and try it out with newer models, local models, and so on. A lot of potential future work here. Different prompts, different exercises. Really look at the prompts. I mentioned which model to use, which metric you want to use. Maybe you are not interested in code complexity. I didn't actually give the results of code complexity in this presentation. Go look at the paper. And I will leave you with this image to sort of prompt your thinking on what counts as fair comparison. And so here we have the bureaucrat saying, to be fair to everyone, you'll all take the same test. Climb that tree. Thank you.